familiar for me. So welcome those who I know and welcome those who I don't. I have a civil engineering background, and I worked for I think 6 years in TU Braunschweig together with Professor Mattis. And hopefully, due to my engineering background, I can help you a little bit to understand how to carry out in practice uncertainty quantification and updating of any engineering model. In this case, we targeted finite element models, but it could be used for other models too. So to get started, this is something that Professor Mattis already explained. There are two types of uncertainties. One is called aleatoric and the other is called epistemic. So as he described, aleatoric is an uncertainty which we cannot reduce. For example, when we throw a dice, we do not know whether it's going to be a 6, a 4, a 5, and so on. This is the same thing with the wind load. The wind load behaves like a stochastic load. So we know its mean value more or less, but it works in an ad hoc way to in a dynamic way. So microstructures can be also considered as aleatoric uncertainty. And this is the type of uncertainty that we cannot do anything with. So the main goal of these lectures is somehow to address the epistemic uncertainty, which is uncertainty that is coming from a lack of knowledge. So, for example, if we have some foundation of an old building, then we do not know the state of this foundation and what's happening below the foundation. There can be water, which is damaging the foundation. And then we do not know exactly the material properties that we can compute with. And this is a type of epistemic uncertainty, which, as this drawing shows, either we don't see it, we don't hear it. So this is something that we can somehow address to reduce by gaining more knowledge, so collecting more information about the phenomena. Even though if we cannot make any test that would somehow damage the structure or it costs too much, there are other types of physical properties that we can measure, and sometimes these measurements can show more information about the epistemic uncertainty that we would like to learn from. So this is what we are addressing today and in the next week, in the beginning of the next week. Now the outline of the lecture, you can see it on the top, the main topics that I will address today. Now I give a small introduction and motivation. Professor Mattis has done that. So I will only add some engineering perspectives and show some more examples. Then I will show you a library package, which works, which is a MATLAB library package, and it's an open source package, so you can download it, but I will show you how. And you can use this library package to be able to carry out all these uncertainty quantification methods that we're teaching here, and also the inverse methods when we are trying to learn more about the input parameters. So I will talk shortly about the library package, and then I go to the basics of probability theory, which was done by Professor Mattis. So this will be really just some detour to show you what you should already know or what you should understand, and give you some literature if you're not familiar with the necessary terms that you will need to understand the theorems. The fourth point is, and the fifth points are two ways of carrying out uncertainty quantification, and I will explain what I mean by uncertainty quantification. And I have way too many slides for today. So it is possible that I'm not going to finish the 5th point. If this will be the case, I will continue this on Tuesday lecture. Okay, so this is the general, sorry, my voice is disappearing. This is a case of a general framework. Now imagine in this triangle, there's some engineering simulation. You can be a mechanical engineer or a civil engineer or a chemical engineer or a computer science guy, or other engineers are maybe also presented. But the main idea that you have some deterministic simulation here. But the problem is that the simulations are getting so advanced nowadays as computational capacity is increasing. So the problem is that these highly nonlinear problems are extremely sensitive to their input parameters. Now, these input parameters are often things that we cannot exactly know. So they have this type of epistemic uncertainty. It's also possible that there are some aleatoric uncertainty too, but now let's not complicate the case. So let's think about this very easy toy example, an oscillating mass. So if I displace this mass from its equilibrium state, it's going to oscillate, and if it's a damped one, the spring, then it's going to somehow stop with time oscillating. But the problem that I don't know exactly the stiffness of this mass and maybe the damping of this mass, and maybe I don't exactly know the exact value of this mass because I don't have the proper measurement device to know it with high precision. In this case, let's say I have two parameters, the stiffness and the mass, which I call Q1 and Q2, and it has a certain uncertainty. And when I talk about uncertainty quantification, I mean that I want to see how this uncertainty of the input parameters is propagating through the response. So in this case, the displacement of the spring. Probably with time, the uncertainties will grow as the oscillation starts to behave completely different after some time. So what I want to know, I want to measure these uncertainties that are due to the uncertainties of the inputs. And this is very important because sometimes even I have a small uncertainty here in the inputs because of the highly nonlinear problem. These uncertainties can be amplified in the solution. So this is something important for an engineer to check how these uncertainties influence their result. So when I talk about uncertainty quantification, I mean in some way quantifying the uncertainties of the unknown function or the response function that I'm trying to get. It could be some statistics like mean, variance, quantize, or I can also have more information when I have a functional approximation of the response, but this is later to come. So the general network, which is in this triangle, this simulation, in general, can be written in this abstract form, something that Professor Matthew showed you. So this is some source term. Q is my uncertain set of parameters. U is the unknown function that I'm solving for example, the displacement of this mass. And the source term could be if 0 if there are no generating force here acting, or it could be just a generating force as well. Such a general description could be a finite element model, which can be written somehow like k times u equals some right-hand side term. In this case, the stiffness matrix K depends on some parameters Q, which could be modules or other material properties, for example. And then U will depend will depend on these parameters. So in an abstract way, I write omega. It means it depends on the actual realization of those inputs Q. So Q is a random variable now. So it makes the response a random variable too, or a random field or a random process. Okay, and this is uncertainty quantification, the forward problem. And the main goal of this webinar is not to do the uncertainty quantification, but to do the inverse. If I can measure the output of the response or some function of the output, for example, at certain times I can measure the position of this mass, then I can learn about these parameters Q1, Q2. And if in the future I want to make predictions, I can reduce these uncertainties, and then the future analysis will be a more exact or a simulation with less uncertainties, which is something that we would like to do. So today we are strictly talking about the forward problem, not the inverse problem. I only mention in the general framework what the inverse problem is, and we see how we can do that. Okay, so this is an example which is similar to the oscillating mass. This is a weather forecast that I plotted yesterday from the internet for Ljubljana's weather forecast. You can see that the temperature is somehow in some way oscillating, and the exact value of the temperature cannot be exactly predicted. What you can see here is a similar model for some temperature variable. And you can see that with the number of the days, how the uncertainties of different models, this is some quantile, some confidence region that you see with colors. And you can see that after 3-4 days, our predictions are completely wrong. So even a small change of the input parameters can lead in a completely different weather after 4 days. That's why usually only short-term weather forecasts are more trustable. But when they do climate models and weather forecasts, they also use this Bayesian inversion to learn more about the internal variables and to be able to give continuously better and improved predictions. So this is the motivation, and this is the general framework of the uncertainty quantification. So how do we do uncertainty quantification? I said we have this general problem, which could be this oscillating mass. And what we would like to know is we would like to know some statistics of the response U. Now, maybe we don't want to know the mean and the variance of the U directly, but some function of the U. Maybe we would like to know stress values if, in case of some beam analysis, for example. So in a general form, I write it with a psi function. So some psi function of U is a random variable, and we would like to know, for example, its mean value or any other statistics like standard deviation and higher order moments and so on. They can be all written with an integral term. So I'm trying to evaluate some integral term in this case. In the case of the spring example, let's say I want to compute the expected value of the position at a certain time due to my uncertainties of the stiffness of the mass and the value of the mass itself. Sorry, the stiffness of the spring and the mass, which can be written as the integral of this displacement, let's say at a fixed time step. And I compute this integral over the interval of the stiffness and the mass. So any values that the stiffness and the mass can take, I have to integrate it over. And here I I weigh this integral with the probability distribution function of m and k. So you see here, I have the product of those two probability distribution functions. And I have here the dm times the dk, but this is only true if m and k. So my two uncertain parameters, they're two independent random variables. That's what Professor Mattis explained. If these two random variables, m and k, are not not independent, then I cannot use Fubini's theorem. So I have to put here somehow the joint probability distribution function and integrate it over the combined m and k parameter space. But this is difficult to express when I have not independent random variables. So ideally, whenever, and I go back to this framework, whenever I have some set of random variables, I want to try to make those an independent set of random variables. So I map them to another set of random variables if they are correlated or dependent, and represent them ideally with Gaussian random variables that are uncorrelated. And if Gaussian random variables are uncorrelated, then they are also independent. So then I can easily compute this expression. So going back to the problem, I'm trying to get this expected value of the u. And as this is an integral term, what I need to do is just simply evaluate this integral. Though I don't know, I don't have an explicit dependence of the unknown function, how they depend on km. So I do not have an explicit description of the u, because it's given in a way like that. So for example, I'm solving it with a finite element method, solving a system of equations. I do not have an explicit form for that, but I can evaluate this integral term numerically, meaning that I compute some integration weights, and I evaluate the function at the integration point, and I sum them, and then I get some estimate of this mean value. So this is in general if I don't want directly some mean value of u, but I want to compute some function of u. Okay, so this is the so-called direct integration, and we will go to the question how we can compute this numerical integration term. A more advanced approach is the so-called response surface method, which means that I'm trying to, though I don't have an explicit form of this, but I try to write it with an explicit form with an approximation. So I want to approximate my solution, which is depending on the parameters q in the spring example, on the parameters k and m. And I want to write it as a linear combination of stochastic basis functions and some coefficients. Okay, so I write an approximation of the response, which is somehow approximates the dependence of the solution on the parameters q. And if I have such expression, I can use it here, but I still have to evaluate this integral term. But the advantage of that these integral terms can take very simplified form when I use a special set of basis functions. I will go inside that, and we will focus on polynomial expansions here. So here, these psi functions will be polynomials. For the spring example, it will be polynomials in function of k and m, the stiffness and the mass. And I have to get these coefficients giving me this linear combination. So this is something similar to what you do in finite element method, that you approximate the solution as a linear combination of basis functions. But here, these basis functions, they depend not on the spatial variable like your finite element model or the time domain, but here this is written in the stochastic dimensions. So if you have two random variables, then you extend your finite element with two dimensions. One is k and the other is m, and then you write an expansion how the solution depends on these two random variables. Now, how I compute the coefficients, I can compute the coefficients in different ways. I can compute it with interpolation or regression, as Professor Mattis explained, or collocation, a general way to say it. Or I can compute it with orthogonal projection. I can also compute it with stochastic Galerkin method, which is typically an intrusive method. So it means that you write this approximation of U as linear combination of basis functions, but now the basis functions depend on the usual dimensions of your finite element code, and you extend it with the uncertain random variables, so in this case k and m, for example. And then in this extended dimensions, you have to solve the Galerkin method. So this means that it's an intrusive method, which for you means that you cannot use your deterministic solver, so your finite element code that you're solving it, but you have to, from the very beginning of the code, you have to completely change the code itself. So when you're using an industrial software for solving with finite element method, then this is something that you cannot, that you do not really have access to change the deterministic code. So this is why the non-intrusive methods are gained more popularity, because they're easier application. The advantage of stochastic Galerkin methods is that you have an error estimate on how big errors you're making with your approximations, and this is something not bad to have. Okay, so this is the general framework of the uncertainty quantification, and this is how a response surface looks like. Now, this is the response surface of the spring example. Now, this is a toy example, and I'm lucky, and I can actually write the position at a certain time of this mass, depending on the value of k and m, explicitly. So there's no problem writing this explicitly, though this system is described by a differential equation, but I can analytically solve for that. So I know how exactly the position of this mass at a certain time depends on the stiffness and the mass, okay? So this is a highly nonlinear surface, as you can see. So I say that due to my uncertainties, because I'm not sure whether the mass takes this value or that value, the response can change from low to very high, as you can see. The same with the stiffness of the spring. So this is the response surface, and when I do a response surface method, I'm trying to approximate this surface somehow. And this is a regression example that you can see. The black crosses are the points where I have evaluated the solution. So I computed what is the position of this mass, let's say at 10 seconds, with different values of the k and the m. So you see these values with the right crosses. And if I compute 4 values of k and m, then I see that I can only get a linear approximation correctly. If I if I know in advance that my response surface can behave widely, then I have to choose more points to gain more information. And you can see how with increased number of points, I can get closer to the true response surface. Okay. Now, other than the response surface method, you can evaluate easily the response at any value of the input parameters in a very computational, cheap way. The other advantage that you can very cheaply compute statistics like mean, variance, and also sensitivities of the position of this mass. So by sensitivities, I mean that often I want to know how sensitive is my solution to the uncertainties, to the deviations of the input parameters, in this case, the K and the M. So often in a finite element model, we have 100 inputs of the finite element model. And in this case, I would like to see which is the input parameter, which can really widely change my response. Because if I have such parameters, I want to learn about those parameters more. If I want to have a better prediction of the model. So that's why global sensitivities are, I think, crucial in engineering practice when you do uncertainty quantification and also when you do identification, to see which are the parameters that can significantly change the output, the solution. And then you only have to fiddle with those set of input parameters, which can significantly influence the output. So with the help of response surface method, you can evaluate these sensitivities very efficiently and very easy. Now, the other part of our task is to do the inverse method. The inverse method means that we have this problem, and what we have is actually some observation y. So this is the response, let's say the position of the mass. These are the uncertain random variables, let's say the stiffness and the mass, and some source term. And the problem now that I would like to make my model better and shrink these uncertainties of Q. And I would like to do that by doing some measurements. Now, the easiest would be to directly measure the uncertain input random variables, so the stiffness and the mass. But now we are talking about problems when there's no way to measure directly those Q input parameters. So maybe I have a measurable operator that depends on these input parameters and the response U. For example, it could be some relative displacement of the mass, because I can measure the position as a distance from the ground, for example. And this is what I call the y. So this y is the observable. This is something that I can actually measure. So this is the information that will teach me about the value of the Q. The problem is that y is some measurement. So in a typical case, a measurement is poisoned with some error, epsilon. So I have here I suppose some additive error, and z is my actual observation that I really measure. So this is the actual measurement. This is something that I can observe, and this is something that I have observed or that I have measured. And unfortunately, there is some error term which I cannot get rid of. So what would be the logical way to do it? I can approach this problem with a classical optimization method. So what I do, I'm trying to invert this observation function. So invert this whole problem and trying to figure out how I can compute from the response the Q. So in this case, not the response, but y. So how I can compute from y the Q. So what I'm doing, I'm actually inverting the forward problem. And from the response, I try to get to the values of the parameters. Now, the problem of this is that this is typically a nilpoise problem, and you can see this on this image. So you see the position of the mass, of this oscillating mass at a certain snapshot. And you can see how it's changing with the value of k and m. So when I observe a value of the position, let's say this 0 point, I don't know how much is that, but where this dark blue plane is shown. So at this height, this is the value that I have actually measured. This is z. I have to put here another plane, which is if this is my measurement. So I could, because of this error term, I could have the true value of y somehow upper and somehow a bit more down, but close to this plane. But even if I knew exactly, if I wouldn't have this error term inside, what I would have is that I cannot get one specific value of k and m. Because as you can see, all these cross sections of the plane with the response surface method corresponds to exactly the same displacement or to exactly the same position of the mass. So when k and m takes values along this line, and along this line, and along this line, and so on, then you get the same position. So this is not a well-posed problem because there's no one solution of the problem, because there are infinitely many solutions of the problem. What you do in a typical optimization problem is to minimize some cost function, the deviation of, let's say, the measured value from the computed value. And because of the ill-posedness, you put some regularization term on top of it. And usually what you compute, as this is not always a well-defined problem, you compute some local optimum, but it's not sure that it's also a unique solution, and it's also not sure that it's an absolute minimum of the cost function. So this is a problem of inverting, for example, engineering system that I showed you, for example, for the oscillating mass problem. Now, the real knowledge that I would have is somehow have all these values of k and m to get those. Now, because of the error term, I do not have these lines as a solution, but I have some regions around these lines that I would like to get. And this is something that you can get with the Bayesian framework. So I will talk about the Bayesian framework later on. But what I would like to point out, especially for Bostian, because he asked me this question, that what is, I note with F, the probability distribution. So this is the probability distribution of the Q parameters given my actual measurement that I measured. And this will be the distribution function, an updated distribution function of k and m, which is conditioned on my actual measurement. So this is the term that I'm trying to get. That would be ideal to get in an understandable form. And the way I can compute it is from the Bayes theorem. And now I'm not going to go into the details, but what you have to know is that this term, the likelihood, what is the probability of getting my actual measurement when a certain value of the parameter is assumed. For this term, I need some knowledge about how my solution and the observable depends on the Q parameter. So for this term, I need to carry out the uncertainty quantification, or otherwise I will end up with computationally extremely expensive methods. So when we are focusing this webinar on identification, you have to know uncertainty quantification as well, even though if you're not interested in what is your uncertainties of the response you due to the uncertainties of the parameters Q, you you can use this knowledge what you have from uncertainty quantification when you have to do the inversion problem. Some other method using some functional approximations is based on the conditional expectation, and I'm not going to go into the details, but now I explained you this whole framework that we are doing in this webinar, and we are only going until the uncertainty quantification today and also on Tuesday. And Tuesday we start with the inversion. But before doing that, there's a lot to know to be able to understand all these different methods. So just to stop my motivation, which went pretty long, I give you a few engineering problems where these methods were used. For example, there was an old water tank that they try to figure out how they have to, whether there's some maintenance they have to do, and what is the condition of this water tank. And they made a dynamic test on this water tank. And there were some uncertainties in, I think in this case, there were 4 input parameters, like some stiffness moduli, some depth of the foundation, some damping coefficient, and so on. And with the help of some uncertainty quantification method, we could draw this response surface or approximate this response surface, and also get a better prediction of the behavior of the mass. So what you see here, with you see, sorry, we had 3 input parameters that were uncertain. These 3 are shown here and here. And I put samples here of the prior distribution. So this is representing my prior uncertainty of the input parameters. The smaller this is, the easier it is to approximate the response surface, and the smaller the uncertainties are. But in this case, we had a quite large uncertainty, and by measuring some dynamical response of the tower, we could reduce these uncertainties to these blue regions. Now you can see that there are some, so this is how you see the updated distribution of the moduli, the foundation depth, and the C parameter. This was the prior uncertainty. So in all 3 parameters, these uncertainties got smaller. But you can see that some parameters could not be identified so well. And this is because probably the response that we could measure did not really change widely with the change of these parameters. So you can identify those parameters that can change the observable function. If your observable is not sensitive to the parameter, then there's no way to identify it. So you can see that there's some really shrink line where the values of F and E can take values on, but in other dimensions you see that the uncertainty stayed big, so not so well identified. But such identification can make the prediction better and can give you more idea whether there's something to do with a tower, an old tower like that, a historical structure. Okay, now the other examples I'm not going to go into because I think it's getting quite late. Just in a few words, so I will come back to this example of a gas platform. So this is a platform on the Adriatic Sea, which is sucking out gas from under the soil. And because of this extraction of the gas, there's a strong displacement of the seabed. Now, because the seabed is moving down, it's a normal thing, so they computed with it. But the problem is that sometimes these displacements can get much larger than the computation showed. So in this case, what you can do is that you collect all the information you can, for example, on the seabed movements, and measuring those displacements, you can learn more about, in this case, what we learned about is the compressibility, and learning the compressibility can help you deciding whether there's some intervention that should be carried out in the next 10 or 20 years. So I can make the problem easy if it's just a compressibility value of the soil, and I suppose that the soil is homogeneous. But I can also say that this soil, because of some faults in the depth of the ground, is not a homogeneous value, the compressibility. So the soil is not homogeneous, and the compressibility is a stochastic, it's not a random variable, but a random field. Then in this case, I'm trying to identify not one value, but a whole field. And this is now some finite element mesh of the soil, where the tower is somewhere in the middle of the region. And you can see that this was some synthetic analysis. This was the true value of not the compressibility directly, but some scaling of the compressibility. And my prior knowledge about the compressibility, that it takes some constant value and it's homogeneous around in all the finite element meshes, and it has some variance. So from a uniform compressibility field, I could get to something very close to the true compressibility field by carrying out a few deterministic computations. So this is really something advantageous to do. And there is some example with an aircraft where there were a bunch of uncertain input parameters, and with the help of some response surface method, we could get sensitivities of the quantities of interest. And this is something very important for the engineers to see how some uncertainties can influence the quantity of interest. Okay, and some other field problem is the climate change on snow load. So how the snow load is changing because of the global change of the climate. And this was carried out by Filippo Landi. I collaborated in this project, and you can see some region of Italy, and using different direct and indirect measurements on the snow load, and using climate models, we could update the snow load in this region. So you can see the mean value of the prior snow load. This came from all the regulations and so on, what the snow load is. And surprisingly, the global warming can result in an increased snow load, which is very dangerous, and it can happen in the next 10 years, as Filippo showed in his analysis. So locally, it can result in increased precipitation, and because of that increased snow loads, which can damage our structures which were not designed for this high value of snow loads. And this was also carried out by this framework that I showed you. Okay, now I'm going to skip this one. So this is enough about the introduction. So to conclude, there's a broad application perspective in probabilistic methods. And as the numerical analysis that you can carry out is getting more and more sophisticated because of the available computational capacity, the behavior of these models, how they can change due to uncertainties of their input parameters, can be way more wild, as in a linear problem. And this is something that we have to know and we have to calculate with. So I think this is one reason, and the other reason that monitoring systems are more widely usable, so you can extremely surprisingly cheaply buy sensors that can monitor different things, temperatures, displacements, or with the all the imaging methods that are available, you can gain much more information about some system. And if you want to use this information, this is the way to do it. Okay, and another remark is that you have to know that the input variables that are uncertain, there can be many of them. So the dimensions of them can be huge. And this is a challenge for all mathematicians and engineers to deal with high dimensionality. And we will talk a little bit about the dimensionality, but this is a problem that we have to fight with. So it means that we have some expensive, sophisticated model, and now we have to do also uncertainty quantification, which involves lots of computation or successive approximate, several evaluations of the deterministic solver, which increases further the computational cost, and somehow this can give quite big challenge in many cases. Okay, so getting to our next part, what we will use in my lectures, there'll be a library package that can be used with MATLAB, and this was developed by Elmar Zander, an ex-colleague of mine in TU Braunschweig. He worked many years on this library package, and in the years that I was in Braunschweig, I also collaborated with him. So there are some packages or libraries that I have contributed, but the credit goes to Elmar Zander. And this code is available on GitHub. This is the link where you can access it. And now I show you the web page that you get when you put in the given web page. So you see this github.com, Elmar Zander agility testing. And you can see the main folders here. And what you can do is the following. Either you're familiar with Git. I don't know if I can ask any questions here, but how many of you are familiar with Git? maybe some of you could turn on the microphone if you're familiar with Git. Okay, if none of you, and if you're PhD students and you're writing code, I highly recommend you to use Git. It's a repository system you can keep in track with your code, and if you make some errors in the code and you cannot somehow make it back, it's an excellent way uh, to do it through your repository, which always stores some snapshot of your actual state of the code. And it's an excellent way to collaborate together with people when you write a code together with someone. But you're not forced to use Git, but you can also download here. So you have to click on this code button, and then you get how to use. So if you don't know how to use Git, I wouldn't go into these details, but you can learn Git, and I definitely recommend you to learn how to use Git. Or you just simply download the whole library package. But you have to know is that most of the important libraries are in this folder sjlib. Sjlib stands for Stochastic Galerkin Library. And what you have to know that there's a startup function right here, and you have two options. Either when you open MATLAB, you open MATLAB directly from this sjlib testing folder that you have downloaded or cloned. And then the startup function will automatically run. Now the startup function will add to the path all the folders that you will need for the computations. So start with that, a startup, and then you have access to all the functions in sjlib that I will mention during this lecture. Now, because of the time, okay, maybe one more question. How many of you is using MATLAB? Is it possible that no one is actually using MATLAB? Ah, I see here the answer is okay, I am. Okay, great. That's happening. Okay, so I'm not going to go in the basics of MATLAB. We don't have time for that. If you're not familiar with MATLAB, it makes it a bit tricky. But we will talk about the theory too, so you can implement these methods. And MATLAB is an application which is unfortunately not open source. So this is a big contra. But I think it's extremely easy to use for engineers because the equations that you write and so on are very similar to the engineering way we write down things, and it's very good for numerical computations too. So this is what we will use now. We had some first attempts to put this library package to some open source application or language like Julia or Python, but we don't have that. So now I'm doing the MATLAB way, and I hope it can teach you too, even if you're not willing to use MATLAB. Okay. Now, going to the third part. Now, this is something that Professor Mathis covered. So I'm really just going to brush over this topic. But there are certain things that you should be familiar with. And this is a list of those things. And I put here some sources that I used here in the slides too, and that I highly recommend for engineers. to get the basics of probability theory, and also you can find information about response surface methods, is the book of Shu, The Numerical Methods for Stochastic Computations. And there are many other literatures, but I decided to give you this because I think it's an engineer-friendly way of interpreting the stochastic computations. Okay, so the highlighted regions are the ones that I'm going to just very superficially cover, and about random fields and joint distributions, marginal distributions, and also more about covariance. We will do it when we do the random field thing on Tuesday. So again, maybe I can try how I can actually draw. So this is expected value. Professor Mathis already explained you there are many ways to put the expected value of a random variable x, but it comes from an integral term where this is some probability measure. Now the simplest is when this probability measure, when we have some continuous random variable with some finite variance, and then this is the preferable version that we will use, that the expected value of a random variable is computed from its integral, where omega is the domain of the random variable, or the support of the random variable. This is the probability distribution function of x, and this is the random variable itself. So this is the integral term that I have to compute to get expected value. Now, these are the notations that you can often meet with. Just simply as expected value of x, or the mu of x, or just mu x, or x with a line on top of it. This all refers to expected value of a random variable. You can also compute the expected value of a function of the random variable. For example, when we wanted to compute the position of the mass u, depending on the random variables k and m, then we simply put here the response u, and we use as a weighting function the probability density of k and m. Now, if they are independent from each other, then their probability density function can be written, joint probability density function can be written as the product of the two densities. And you can also compute higher moments by taking the integral term weighted with the probability distribution function of the governing uncertain random variables. So you compute the expected value of some power of the random variable. So if this is 1, this is the expected value. If this is 2, this is the variance. If it's 3, it's the skewness. And if it's 4, this is some kurtosis, which I cannot pronounce correctly probably, but please excuse me for that. Okay, now here the mean value is not subtracted. So in the original version, it is subtracted. So I call them centered moments when you subtract the mean value. So for an example, this is the variance of the random variable x, which, due to the linearity of the integral term of the expectation operation, can be written as the variance of or the expected value of the squared random variable minus the squared mean value. Okay, now numerically, this is not the way to compute it because of cancellation error, but this is another question. Now, the standard deviation is computed from the square root of the variance. Okay, so Angelica asked what you use the higher moments for. For example, skewness gives you or characterizes the asymmetry of a probability distribution function. So you can see that this is the mean value of this random variable with this distribution function, and this is the middle of the region. So you see how skewed this density function is. Now you can have negative skewness and positive skewness, and you can see these two directions here. You can also evaluate the fourth moment, which is this ugly word, I'm sorry, kurtosis, which shows you how peaked a distribution is. So it gives you some ideas about how these probability distributions look like. Now, there are more complicated distribution functions. For example, if you have a B-model distribution function, let me get a pencil, if I can. Just a second. So if I would have, I can only have lines here, sorry. It's ugly, but why not? So if my probability distribution function looks like that, then it's more difficult to treat, of course, this type of distributions. For example, even the expected value gives me something where the probability is low, which is not very advantageous. And also it's more difficult to somehow characterize them with the help of these moments, but they can help. Okay, now the characteristic function is something I'm not going to go into. This is what you need in order to, we will go to the central limit theorem. Now to prove the theorem, you will need the characteristic function, but I'm not going to prove it now. So if you're interested in the details, you can go through the slides or the shoe book, the basics of probability theory part. But it's just an inverse Fourier transform of the random variable. So this is not a function of x anymore, but a function of t. And it's also a way to describe a random variable. Now, this is an example of the most important random variable copied here from Wikipedia. So this is the normal distribution with different parameters. So the normal distribution is written or noted with an n letter, where this is the mean value and this is the variance. And you can see that it's characterized by the probability distribution function, a cumulative distribution function, and these are the most important parts. And by knowing the mean and the variance, so it is very good that the normal distribution function is actually characterized by only these two moments. So you don't need further ones because all the other moments are zero. So it makes it easy to handle. And also only normal, standard, not standard, but normal random variables have the advantageous feature that when they are uncorrelated means that they are also independent. So that's why we like to work with them, Gaussian random variables. Okay. Okay, and the covariance, just for those who do not know, now the covariance function, if I have two random variables, x and y, then the covariance is a matrix, a 2 by 2 matrix, if I have two random variables, where in the diagonal you have the variances of x and y, and you have these mixed integral terms in the co-diagonal. Okay, I will talk about the covariance more when we go to random fields and random processes when you don't have one random variable, but you have a set of random variables. But this is all I wanted to show right now. Now there are many notations or definitions that you have to know when you talk about random variables. For example, when do I say that one random variable is equivalent to the other one? And I'm gonna skip this part. So please, if you're interested in this topic, read it. What it means, almost sure equivalence or equivalence and so on. But I'm going to skip this part and the convergence part because we do not have time for that. Now this is important, but only in small detail. And now I check the time that I have. Oh, not much time. Okay, so this is the Chebyshev inequality, which gives you the relationship between probabilities and expected values. So if I choose some value of an A, if I have unfortunately, I cannot draw like a free line. Where can I? Oh, maybe I can. Okay, so if I have a probability distribution function and I have some value here that is A, sorry, it's a bit ugly, then I want to see what is the probability that that I have here, that A will exceed this value. And I can express it as a function of the expected value. Now, this inequality and another inequality, the second Chebyshev inequality, helps me to form the weak law of large numbers. So sorry for skipping all this theory part, but I try to come to the main parts. And if you think you better, if you cannot understand it like this, you should go back to the basics and read it. But I try to give you the main ideas. That when I want to get the expected value of a random variable, so for example, in an engineering matter, if you want to get some expected value of u because of the change of the input parameters k and m, a general way to attack the problem is that you compute u, the solution, with many different values of k and m. So you just sample from the distributions of k and m and compute the solution for all those values and take the average and you say this is the expected value. So this is not a bad idea, I have to say, and this is the brute force approach to handle the problem. But what I try to get as a take-home message is that how much you can trust this brute force method and what you can expect from it. I think often it can happen that there's no other way than computing expected value from many samples and take the average of it, but you have to know what you're doing and how big error you may do. Okay, so this is the intuition that if I have a random variable x, I can approximate its expected value by taking lots of samples and taking the average of it. Now, in order to see what it can do, I introduce you a new random variable. And what I do a trick. So I put here a capital X. So I forgot to mention that often a random variable is written with a capital letter, and one realization of it is written with a small letter. So this is a random variable, and this is just one realization of X. So what I'm doing here, I'm replacing the realization to the random variable X. So I say that as many samples I have, as many random variables I introduce, and I say that they have the same distributions and they are identical, and so they are they are independent and identically distributed, which is abbreviated by this IID. So I put here a random variable and I say how this random variable behaves. This is an estimator, which is estimating the expected value. If I take one sample of this mu random variable, then I get one realization of this estimate. Okay, so this is important that this is a random variable because I changed this to be a random variable. Now what I can show with the different theorems, and this is why you have to go, if you want to understand, you have to go through all these inequalities and so on, and all the convergence types, is that the variance of this new random variable is actually this expression right here, where sigma is the standard deviation of the original random variable x, and n is the number of the samples. So actually, this is an estimator, that I call it an estimator, which is a random variable, which has a variance sigma squared over n. So the larger this number is, the smaller the variance is, and the smaller the standard deviation of the original random variable is, the smaller variance I will have for this estimator. Okay, so this is what I can prove, that in probability. So the probability that the estimator will have zero mean is sorry, that the estimator will get close enough to the mean value is bounded by this term. So the more number of samples you have, the bound is smaller, and the smaller the variance is, the bound is the smaller. Okay, and furthermore, the central limit theorem shows, and now in the back of these slides you will find the improve of that this estimator with n in the limit of n will tend to be a Gaussian random variable. So the estimator itself is a Gaussian random variable. And now we are still with the same topic, and see how we can compute the expected value of a random variable with the library package SGLib. So what I show here, and I'm not going to go deep into the details, but these are the basic functions that you can use. So I'm using here to define distribution by the GenDiscreate function, and I will show you later on that you can use it in a much simpler way and a more direct way, but these are the deep down functions that SGLib is using. If you really want to understand every step of SGLib, you have to go down there, but you're not forced to, so it depends really up to you how superficially or just as a user you want to use it, or how much you want to understand it. But this is a code which is easy to understand, so you can also learn the theory by understanding the code. So I'm defining two random variables with two different distributions. Both of them are normal, but they don't have to be normal, with the same expected value and some different sigma standard deviation. So one has 3 and the other one has half. And here I show that there is a folder in SGLib called statistics, and you can find here what are those distributions that are available. So here you see the normal, And if you see here the normal, it means that in the statistics folder, there should be a normal CDF, a normal inverse CDF, a normal moments, and a normal PDF function. So if you want to know what you can put here as distribution, you can check this folder and you can learn which distributions are available in the existing library package. So now I initiate the memories for some estimators of the mean value and the variance. So what I want to know, I will sample from these distributions, and I want to know if I collect more and more samples, what I get from the estimation of the mean value and the variance. So now I'm focusing on the mean value. Please look at it at home, how the code is formulated. I'm sampling from it, and I'm taking the mean value, and I do it in a loop. So I do it several times for different values of n. The numbers of n are 2, 4, 8, 16, and so on, the powers of 2. And I see how my estimation for the mean value is changing with changing numbers of the sample number. So with the inside loop, I get one of these realizations of the estimator. And this is the error of the estimator. So I already subtracted from it the true value. Now what you can see is two things. One thing is that the error gets really big when the number of the samples are really small. The other thing that you can see that the blue, the second distribution, which had the smaller standard deviation, makes smaller errors. They both have the same mean, so the relative errors they make is much smaller for the blue one because the standard deviation of the random variable was smaller. And we learned that the estimator is a Gaussian distribution. So I could draw here, maybe with another color. At some point, I could draw here a Gaussian. And you see that when I estimate the mean value, I get some realization of, so for the red distribution, I get some realization from this normal distribution. The higher the sample number is, the more I'm approximate, or I have a realization of a Gaussian. So now the take-home message is that you can get very unlucky with the Monte Carlo method. So when you want to evaluate a mean value by average of the samples, depending on the actual realizations, you see that there are many zigzags here. So you can get very high values even when the number of the sample is big, because you have a sample from a Gaussian distribution. A Gaussian distribution is not bounded, so it can go from minus infinity to positive infinity. It means that if you get bad luck, you can have an estimator which lies somewhere here, okay? Now, the less probability you have, the higher number of samples you have, because here the probability of getting a value here is really small, but you still have a chance to get a value there. And this is a very important thing. Okay, so now it's 1 o'clock, and I haven't started the direct integration and the response surface method. So I would like to ask specifically from Bostian whether we can make this session longer, or I just finish this on Tuesday. Sorry, I don't see comments now. Is Bostian here? Okay, so it seems next time you may want to connect with. Okay, good. Okay, but can you just write me whether should I continue or should I stop here and then continue on Tuesday? Okay, I do that. So maybe I just summarize. Okay, I just need 2 minutes to summarize. Okay. So summarizing, I would like to point out that a way to compute, a way to compute, let me show you this slide. Here, a way to compute the expected value of, let's say, the position of this mass is to sample from the parameters k and m, make lots of samples, and then take the average, and then you get an estimate of the expected value. And according to the central limit theorem, what you will get as a value is a realization of a normally distributed random variable, which has variance sigma sigma squared over n. So you are more probable to make a mistake if your U solution has a huge standard deviation or variance, and if you don't use enough sample points. And even if you use enough sample points, the convergence is very, very slow. So it goes with 1 over square root n, the convergence, and even then you can get bad luck and get a really bad realization of this Gaussian random variable and have a big error in your estimation. And that's why we will go to more advanced methods to estimate the expected value and other statistics. And this is to come on Tuesday. Okay, any questions or comments? Or you cannot, but you can write. I know you cannot speak, but you can still write. So I would appreciate comments if the slides are too slow, too fast, average, understandable, not understandable, or if you need any help on explaining something that was not clear from the lectures of Professor Mattis, you can send me an email, and I can, here I write my email address so you have it. It's N. Wildman. Okay.
I think one message is coming from Uroš. One question. But before it comes, let me thank Noemi for this lecture, and also Professor Matthias. Uroš, are you posing a question?
Let me think. Is it possible to get the transparencies? You mean the slides? What does it mean, transparencies?
The slides, yes.
Yes, or I don't know, Boštjan. This is
I don't have your slides.
okay. I uploaded, but I can send the slides too, so it is possible. It's not up to me.
Maybe you can send them to me, and then I will distribute
okay.
them to all the participants.
Okay, great.
Mm-hmm.
Okay, did I go too slow? Because I really thought that there are some things that needs to be explained, and
it was fine for me. I don't know for the others.
Okay.
But for me, it was perfect. So
okay, but I try to be somewhat faster for next lecture of mine. Okay. Great. So have a nice afternoon, and thank you all for the participation. And I hope you learned something. And you have the weekend, so I will send these slides, and I will give you on Tuesday some home assignment. You can already take a look at that and experiment with that. And it would be nice if you could download the library package and get some practice from it. So if you have access to the slides, you can see in the slides there will be many examples, and you can try them. And okay.
Thanks, Naomi, for lecturing, and also we are thanking Professor Matisse for lecturing, and also the audience. Next time you